All right, let's take a look at the next one. Problem 26 is an excellent problem to look at for the definition of a volt. If 1 joule of work is required to move 1 coulomb of charge between 2 points in an electric field, find the potential difference between the 2 points. So the definition is that the potential difference is the work done per unit charge. So you have 1 joule of work pushing 1 coulomb of charge. 1 divided by 1 is 1 volt. So a joule per coulomb is a volt. So this is 1 volt. And as a reminder, potential difference V is the work done pushing a charge at a certain distance through an electric field. If you remember this statement, you will always have the entire concept. All right, let's take a look at another one. Problem 33 looks like a very complicated problem, but in reality it's actually very simple. 2 parallel plates are separated by a distance of 1 times 10 to the negative 3 meters. Are charged to a potential difference of 12 volts. An alpha particle with a charge of 2 elementary charges is located at a point P in the region between the plates. So let's see what information is given, and you can see that's already highlighted. So the distance between the plates, D, is 1 times 10 to the negative 3 of a meter. You have a potential difference of 12 volts. Now you may not be familiar with this symbol yet because we're going to get to electric circuits in the next chapter, but this is the potential difference. It's also what you would call the voltage of a battery. All right, it's 12 volts. That's your potential difference, V. Now, an alpha particle, you think to yourself, oh wow, I have to go back all the way to chemistry and remember all those particles, but you really don't. An alpha particle, even if you forgot what it was, is simply told to you as some kind of particle with a charge of 2 elementary charges. Well, it just turns out that it's a helium with its electrons knocked off, so it's the 2 protons. And it has 2 elementary charges as its charge. So its charge is 2Q, or 2 times this. 2 times this. 1.6 10 to the negative 19 times 2. The question asks, the electric field between the plates will cause the alpha particle, starting from rest at point P, to do something. And what is that something? Well, if it's a positive 2, that means that at point P it will be repelled from the positive plate and it will accelerate towards the negative plate. Remember, it's in an electric field, and electric fields accelerate charges. That's it. Now let's look at the next part to this question. This is a little math. They want to know what is the magnitude of the electric field intensity between the plates. All right, so we go back to our definition. Now, I'm going to move me to the corner so you can see the math better here. Where does this ED formula come from, this relationship? So, V is defined as the work done per unit charge, but work is force times distance. So, if force times distance is now replacing W, but you regroup the force divided by the Q, that's where you get your E from, and you have ED. So you were given the values for V and D, and you could solve for E by itself. So E equals V divided by D. See, E is here, and it's multiplied by D, and that also equals V potential difference. So dividing this D all the way back to this V, under this V, E equals V over D. 12 divided by 1 10 to the negative 3 gives you 1.2 10 to the 4th volts per meter. So that's another way of expressing the electric field intensity. Instead of newtons per coulomb, you can also see that it's expressed as volts per meter. Okay, let's take a look at another problem. Here's another question about the multiples of net excess charge. A sphere has a net excess charge of negative 4.8 10 to the negative 19 coulombs. The sphere must have an excess of how many? Something, electrons or protons. Well, 4.8 is a multiple of 1.6. So it represents 3 electrons. Each electron is 1.6 10 to the negative 19th per coulomb. Multiply that by 3 and you get 4.8. The fact that the number here is negative implies that it must be an electron. If it was positive, it could be 3 protons, but it's the negative makes it 3 electrons. See? Very easy. Let's look at another one. Here's a problem about a moving electron. A moving electron is deflected by 2 oppositely charged parallel plates, as shown in the diagram. The electric field between the plates is directed from. So now you look and you say to yourself, how do I know? Because the original diagram only shows me the deflection path of the electron, and it doesn't have these pluses and minuses with these arrows. So it's this simple. Electrons are attracted to the positives of the positive plate. So as it goes through, it's being attracted or getting closer to plate C, point C. So that has to be the positive. And of course, it's being pushed away from the negatives. So if I was to draw an electric field, it would have to go from plus to minus. And here are my blue arrows pointing from the positive plate to the negative plate. All right, that's it. And this concludes our summary of the electric field formulas and applications that were in this exercise packet. Thanks for watching.